Hello everyone, this is Dr. Lennon. So let's continue with profit, cost, and revenue and see how that relates to our applications of local and global extrema. So let's recall if we have profit, which is just defined to be your revenue, the money coming in, minus the cost, money going out. A natural question is, when will profit be maximized? So with our knowledge of finding extrema using the first derivative test and also the extreme value theorem, typically what we do is we'd write our function. So we could write our profit as a function of quantity of items sold or produced. And that's going to be our revenue function, R of Q minus C of Q. And that optimal point would occur at a critical point, wherever the derivative is going to be equal to 0. So if you take the derivative of both sides, we know that the derivative of a difference of functions is just the derivative of each one separately. So we have P prime of Q is R prime of Q minus C prime of Q. And then we want to maximize profit, so we'd set that equal to 0. We have R prime of Q minus 0 equals R prime of Q minus C prime of Q. Well, you could add C prime of Q to the other side, and we would get C prime of Q equals R prime of Q. And remember, the derivative of these cost and revenue functions is also known as the marginal, or it's our grade estimate of the marginal, how much it costs or how much money comes in from producing an additional item. So our conclusion here, so hence the profit is maximized when marginal cost equals marginal revenue. So there's really nothing new here in terms of math. It's just the particular setting and sometimes the language that they use in these business applications or economics applications. So let's just go ahead and look at a straightforward example. Let's say we want to find the quantity which maximizes profit if the total revenue and cost are given by say R of Q is the quadratic 5Q minus 0.003Q squared, and C of Q is 300 plus 1.1Q. So that's just a linear cost model. So the cost is increasing linearly and the revenue is following a quadratic pattern. And again, we have some domain restrictions here. So these models are accurate when Q is between 0 and 1,000 units. So the question here is, what gives the minimum profit? So that's actually a good point. I assumed maximum, but it really does depend on your model. So up here when we said hence profit is maximized, really it's optimized. So it could be maximized or minimized depending on what your models look like. So it might not be that your profit is maximized. It could actually be minimized depending on things like whether your revenue is increasing or decreasing with respect to things like cost. So here, if we think about that, our revenue is going to be, well, it's a parabola open downward. We'd have to think about where the vertex is. So the vertex would be negative b over 2a. So that would be negative 5 divided by 2 times this negative. So it would be some positive value. So the revenue is increasing, but probably more slowly because it's going to have a negative second derivative. Yeah. Anyway, so we know that this maximum or minimum value, the main way that we would go about testing for something like that, right? We would find the critical points, and then we would set up critical value regions, and we would see whether or not the derivative is changing from positive or negative. That's how we go about doing things, so we don't have to think about doing too much in our head. The same process is going to go ahead, and then we can just look at test value regions to determine if what we're looking at is a local max or local min. So again, we're going to go through the same process here. Set R prime of Q equal to C prime of Q. So just let's keep in mind, and solve. So this is the same. This is equivalent to setting P prime of Q equal to 0. But a lot of times the problem is written in such a way where revenue and cost are given, so sometimes it's a little bit simpler to just think set R prime of Q equal to C prime of Q. Okay, so what is the derivative of revenue? Well, the derivative of 5Q is 5, and we use the power rule on the second part, so 2 times negative 0.003 is negative 0.006, and then it's just Q to the first power. The derivative of the right-hand side, 300, is just going to vanish, and the derivative of 1.1q is just 1.1. So we have this linear equation that we want to solve. So what do? Well, let's go ahead and subtract 1.1 and add 0.006q, and then that will move to the regular numbers to the left and the q's to the right-hand side of the equation. So we end up with 3.9 equals this 0.006q, and we can go ahead and divide by 0.006 on both sides. And so this gives us a quantity of 650. So that tells us what gives the minimum profit. So our conjecture is that this is going to be giving us the minimum profit. What kind of thing do we have, though? We actually have a continuous function on a closed interval because we have Q going from 0 to 1,000. So what we can do is we can set up our profit function and then test the 3 critical points. So basically we have one critical point, or one critical value, Q equals 650, and 2 endpoints, Q equals 0, and Q equals 1,000. So basically we need to check what is the value of the profit at each of those 3 points. So let's remember that our profit function P of Q is just R of Q minus C of Q, which again is just going to be plugging in those 2 formulas. So we have 5Q minus 0.003Q squared minus 300 plus 1.1Q. We want to be sure to keep that 300 plus 1.1Q in parentheses. So our profit function can be simplified to 3.9Q minus 0.003Q squared minus 300. So then we want to use the extreme value theorem to check those 3 points. So we want to plug in P of 0. We want to plug in P of 350, our critical point. 650, not 350. And then we also want to check 1,000. So plug these 3 numbers into the profit function above. So the first one would give a profit of negative 300. So you lose money if you don't make anything. That makes sense. Those would just basically represent your fixed costs. Then you would have 967.5. So it turns out that this is actually going to be our largest value. And then we have 600 at 1,000. So probably you could have guessed that, but basically our conclusion here is the minimum profit occurs when the quantity produced is 0 units, and we could say the fixed cost or initial cost are 300. I don't believe they give us any units here, so we don't have anything there. And also our critical point actually turns out to be the maximum value as well. So it looks like our maximum profit is going to occur at 650 units produced and have a profit of 967.5. So this is going back to the extreme value theorem, which says if you have a continuous function, which the profit function is a polynomial function, a quadratic, so it's continuous, on a fixed interval, which was 0 to 1,000, then your function is going to attain both an absolute max and an absolute min. So we see our absolute max is at 650 and our absolute min is at 0. So that's it for this example. Hello everyone, this is Dr. Lennon, and it looks like there was a little bit of a problem. So I've already written down all the stuff, so we're just going to go through it with a recording. So basically in this next example, we've got the revenue that's given by 625Q and the cost given by 10,500 plus 4.8 Q squared, and they want to know what quantity is profit maximized and what is the profit. So again, just like the previous example, we want to take the derivative, set marginal revenue equal to marginal cost, and solve for our critical point. And so the derivative of R of Q is just 625, giving us the left-hand side down here, and the derivative of C of Q, the 10,500 goes away, and we just get 9.6 Q. So to solve that, we just divide by 9.6, and we get the maximum profit of 65.1. So to figure out what that actual profit is, what we want to do is figure out our profit function and then plug that in. So P of Q is just the original revenue, 625Q, minus the cost function, 10,500, minus 4.8 Q squared. Again, that needs to be put in parentheses, and then we can go ahead and distribute the negative sign, so we get the profit function, and then plug in the critical value, 65.1, and we get our maximum profit of 9,845.05. Again, we know that that's got to be a maximum, because if you look at the P of Q function right here, this is a quadratic opening downward. So because it's a quadratic opening downward, that critical point is going to be the vertex that's on the very top of a shape that kind of looks like a hill. You could also use the first derivative test value region method that would tell you, okay, it's increasing left of the critical point and decreasing right of the critical point. That would work as well. The next question is interesting because we have a musical theater. So they're selling for $10 a ticket, and they know that will sell out the theater that has a capacity of 1,300 people. But they also know that if they charge an additional $1, the sales decrease by 65. So the question is, what actual selling price would maximize the revenue? So just because it's sold out doesn't mean you're actually making as much money as you can. So what you want to do is let X represent the number of price increases. So your price function is 10 plus X, and your attendance function is 1,300 minus 65 times the number of times you raise that price. So your revenue function is if you take your price and multiply it by revenue. So you get a polynomial. So basically to go from here to here, we just want a FOIL, right? That will give us, and then I write it in increasing order. So X times minus 65X is minus 65X squared, and then you get minus 650X plus 1300x, which gives you the middle term of 650x, and 10 times 1300 is 130,000, or excuse me, is 13,000. So then we want to take the revenue of that function. So the 13,000 goes away. 65x squared has derivative minus 130x, and then the derivative of 650x is 650. So we can solve that equation. It's just a linear equation. So I just add 130x to both sides and divide by 130, and we get x equals 5. So remember, that's the number of price increases, not the price. So right here, this is the, I plugged in both values. So this is revenue for sellout, and this R of 15 is the revenue at the critical point, right? Because if I have 5 price increases, that means my ticket price is $15, so that's why I'm doing 15, and then the other part of the function is the attendance, 1,300 minus 65 people for every $1 price increase. So we're losing about, let's say, 325 seats, but our revenue now is $14,625 compared to a revenue of just $13,000 for a sellout. So it actually makes more sense to raise the prices if you want to have a higher revenue. All right, and then the last one, we have a landscape architect that they have a 3,000 foot rectangular region, square foot rectangular region, and they want to put shrubbery around 3 sides of it and fence around the 4th side. So if it's a rectangle, it has 2 different length and a width, so call one of the sides X, one of the sides Y, and then the 3 sides I've shaded, that's representing the shrubbery. So one thing you can do is you can solve for Y, because in order to take derivative, it's easier if we get down to one variable. So if X times Y is 3,000, Y is just 3,000 divided by X. So our cost, we have $10 times X on the one side, and then we have $45 for the shrubs times the X plus the 2Y. So if you just multiply everything out and simplify that function, we end up with 55X plus 270,000 over X. So for taking the derivative, it's a bit simpler to write that as 270,000 times X to the negative 1. So the derivative of 55X is just going to be 55, and the derivative of 270,000 X to the negative 1, we bring that negative 1 down and then lower the exponent by 1. So it's minus 270,000 X to the negative 2, which we can solve by adding that term to the other side. So 270,000 over X squared equals 55. We can cross multiply, and we get 270,000 equals 55X squared. Divided by 55, X squared is 54,000. And then we only have to worry about taking the positive square root here because X is representing a distance, which has to be positive. So X comes out to about 70.06 feet. And we need to plug that in to the original cost function. So the question asks for find the minimum total cost. If you want to find the dimensions, I plugged in. So basically, these right here are the dimensions that minimize cost. And to figure out the minimum cost, we can use any of the cost functions that we've written down. So I just used the very last iteration of it, where we do 55 times the X value, 70.06, plus 270,000 divided by 70.06. So we get a minimum cost of $7,707.14. So that's it for this example. So hopefully those were pretty straightforward applications of optimization to profit, cost, and revenue. So this is Dr. Lennon signing off.